Shear needs to be checked for every reinforced concrete beam. If a beam isn't designed properly for shear, shear cracks close to the supports can occur, and in a worst case scenario, these cracks can lead to a collapse of the beam. So in this video, you learn the 5 steps to design and verify shear reinforcement of concrete beams. And if you stick until the end, I'll show you some practical examples of shear reinforcement and what you need to consider when you need to transfer shear between different elements. So let's get into it. As an example, we'll use a beam cross-section with a height of 550 millimeters and a width of 300 millimeters. We designed the shear reinforcement for a shear force of 450 kilonewton. There are different approaches to the steps we do in the following. We're going to verify the diameter of the stirrups, but you can also choose to verify the shear capacity. This is up to you. In step 1, we define the concrete and reinforcement properties of the beam. Here on this slide, you see the concrete and the reinforcement properties we use in this tutorial. Step 2, the lever arm or effective height of the longitudinal reinforcement is calculated, and that is the distance of the center of the reinforcement to the top or bottom fiber of the cross-section, which is in compression. In our case, with a positive bending moment, it's the distance from the bottom longitudinal reinforcement to the top fiber of the section. For a diameter of the longitudinal reinforcement of 25 millimeters, the stirrups of 10 millimeters, the lever arm is calculated as 498 millimeters. From the picture, we see that we use 4 longitudinal rebars, which have an area of 1,963 square millimeters. The cross-sectional area of one stirrup with a diameter of 10 millimeters with 2 vertical rebars is calculated as 150 square millimeters. The design value of the shear reinforcement for members requiring shear reinforcement is calculated as 479.1 kilonewton with the following properties. In step 4, we verify that the shear force is smaller than the design shear resistance with shear reinforcement. A design shear force of 450 kilonewton and a shear resistance of 479 kilonewton leads to a utilization of 94%, which means that it is verified. As a last step, we'll calculate the spacing of the stirrups. First, according to formula 6.8, we'll reduce the design yield strength of reinforcement to 440 megapascal. The required cross-sectional area of the shear links is calculated also with 6.8 as 913.7 square millimeter per meter. The shear reinforcement, which is the stirrups, is vertical. Therefore, alpha is set to 90 degrees. In the next step, the maximum spacing is calculated as 373 millimeters. And we therefore set the spacing of the stirrups to 250 millimeters. The required cross-sectional area of the shear reinforcement of one stirrup is calculated as 228 square millimeter. The required cross-sectional area of one stirrup is therefore 414 square millimeters because one stirrup has 2 vertical rebars, and the required bar diameter is therefore 6.8 millimeters. Now we can draw up the cross-section and the beam with the shear reinforcement, which are stirrups. Now we could reduce the stirrup diameter from 10 millimeter to 8 millimeter, or just leave it to have some extra capacity. In general, I always like to have some extra capacity. It oftentimes saves you and your design when design changes come from, for example, the architect or the construction company. If they forgot to tell you that actually the live load is changing from 1.5 kilonewton per square meter to suddenly 3.0 kilonewton per square meter. Another thing you can optimize is that you actually increase the spacing in the center of the beam, because that's where actually um, the shear force is much smaller than actually close to the supports. Now let's look at some examples of shear reinforcement connecting two elements. Shear reinforcement are usually vertical rebars. To account for the correct anchorage length, usually closed stirrups, L-shaped or U-shaped rebars are used. Now, when you connect two elements with each other, like for example a foundation beam and a slab, from my experience, construction companies usually rather use L or U-shaped rebars instead of closed stirrups. Another example is if your beam is very tall, it also makes sense to split up the closed stirrups into two U-shaped rebars to account for tolerances. In one of my projects, the foundation beam was almost 2 meters tall. Imagine having to bend a closed stirrup that is 2 meters in height, precisely as the rebar schedule says. That's basically impossible. Before deciding on which shape of shear reinforcement you use, ask the contractor which they prefer. They really appreciate structural engineers that think about their work, and a good partnership can be built upon that. Try it out.